In this video, we'll talk about the substitution method for solving indefinite integrals. Let's recall our indefinite integrals from before. The point was we wrote the integral of f of x dx was written some capital F of x plus c, where big F was some antiderivative of little f. That is, if big F prime equaled little f. This was our idea of an indefinite integral, setting up things like this. And we had a lot of rules for this. Things like the power rule. So the integral of x to the n was x to the n plus 1 over n plus 1 plus c for n naught minus 1. If I integrated, say, e to the x, I would get e to the x plus c. And many other rules like that. Trig functions, sums, those sorts of things all had rules that we could use to find indefinite integrals of functions. This is our new notation for antiderivatives, and we know how to find those just by undoing the rules for differentiation. Now, there aren't many more rules because we've already covered for actually trying to solve these problems. We really have our techniques instead. The main point here is that we don't have things like the product rule and the quotient rule. The issue here is we don't really have ways to combine simpler integrals we know into more complicated ones. So for instance, things like the antiderivative of x times sine of x. I know how to find the integral of sine of x, it's minus cosine. I know how to find the integral of x, that's x squared over 2. But I don't really have a way to do this product. I don't really have a technique for this yet. There is one that you'll get to much later, it's called integration by parts. But there's no technique for products like this. The same goes for something like the integral of now sine of x over x. Again, no way to handle this. There really even is a technique for this one, because there's also the option of things just not having nice integrals, which is an entirely different discussion. But there's no way to combine these things into more complicated derivatives. What we're going to learn here are techniques or ways to sort of manipulate integrals into other integrals that might be easier to solve than the ones we had in the first place. And the first one of those we're going to do is called the substitution method, which comes from the chain rule. So basically, this method is going to be the inverse of the chain rule. So going backwards on the chain rule differentiation to give me an integral rule. Look at an example. Let's see if I have a function f of x that is sine of x to the fourth. Well, how do I take this derivative here? Well, if I differentiate this, this is going to be cosine of x to the fourth, and then times a 4x cubed by the chain rule. Because x to the fourth is on the inside, that's the derivative of x to the fourth. So what does this tell me? Well, this tells me that if I were to integrate 4x cubed times cosine of x to the fourth dx, I should get sine of x to the fourth plus c. Because the derivative of sine of x to the fourth is 4x cubed cosine x to the fourth, this is how the relationship should work. But now how can I identify this as something that would integrate over here? And the idea behind that is the substitution method, because how can I rewrite this integral here on the left? This integral can be written as the integral of some function f of u of x times u prime of x dx for u of x being x to the fourth and my function f of u being cosine of u. So I'm identifying this integrand here as a composition times the derivative of the inside function, and then just by the chain rule, this should give me f of u of x plus c for f, an antiderivative of little f, because the chain rule sends me back this way. That right there is the idea behind the substitution method. This method says the following. If u equals g of x is a differentiable function, then the integral of f of g of x times g prime of x dx is the same thing as the integral of f of u du, which integrates to f of g of x plus c for f, an antiderivative of little f. The important thing here is noting how do you figure out what this g should be here, and knowing that it's differentiable where it needs to be for this method to work. So another example, I want to compute the integral of 2x times sine of x squared dx. Well, here I can see if I set my g of x here to be x squared, then g prime of x is 2x, and I see exactly what I need here. What I see is the integral of sine of g of x times g prime of x dx, which then equals the integral of sine of u du by my setup, which gives me a minus cosine, plugging in my g of x for the answer there. So that's the basic idea of the substitution method and how it works for evaluating simple types of indefinite integrals like this.